Hello, AP Calculus AB, and welcome back to our Topic 6 discussions. We're actually on to our second to last video for Topic 6. These last two videos, day 87 and 88, are going to focus on solving differential equations. Now, we discussed last class when we introduced slope fields and solutions to differential equations that certain differential equations are much harder to solve than others. And so all we're going to do in AB is learn one technique to solve differential equations, and then as you progress in other mathematical courses, you'll learn other techniques. So what is our technique called? Our technique is called solving differential equations using separation of variables. Sometimes we call these separable differential equations. Now, the steps for this can actually be a little bit long, but they're not crazy complicated. And so most of today is really just going to focus on getting you guys some practice. And so as we go through this video, I'm going to skip a few problems that don't focus on the separable differential equations, and you guys can check my work on Teams. But then the ones that do solve differential equations using separation, I will go through. All right, how do we do this? Well, the key is in the name. Separable differential equations. A differential equation can always be written with dy dx instead of y prime. And when we write a differential equation using dy dx, then it shows us that we have two separate differentials here. And although we treat this as one fraction, we've seen before that we can manipulate these differentials to move them to different sides of the equation. We saw this back in our U substitution videos. So how does that help us? Well, what we're going to do is we're essentially going to create two different expressions. One expression is only going to have the output variable, in this case y, and one expression is only going to have the input variable, in this case x. And what's going to happen is we're going to essentially treat this as two separate problems from the beginning. We are going to find the antiderivative of all the stuff with y and the antiderivative of all the stuff with x. So what I'd like you to do right now, please, is pause this video and work through your notes, because I've actually shown all of the work on this left side. And you might say, wow, that's overwhelming. It's because I showed more steps than you would probably show. But what I'd like you to do is on the right side, go through and annotate or explain how I went from one step to the other. Right? How did I go from here to here and then here and so on and so forth? If you get stuck, you can always unpause and I'll go through it with you. But if you feel pretty confident after this, then skip this section and we can move on to the end of this where we'll do a little conclusion and then you're on to your practice. That's how quick our notes are for today. So go ahead and pause me and we'll see what you can do. Okay, you're back. Well, let's actually look at the whole problem first and then start to break it down a bit. And I apologize, there are going to be a bunch of bells ringing. Our classes are very short today and I'm recording in the middle of school. So, write an expression for y equals f of x, right? Our solution for a differential equation is always in the form of y equals something with x. By solving this differential equation, okay? And then it also gives us an initial condition. It tells us our solution better pass through the point 3, 25. Well, the very first thing I do is I start by breaking apart this differential, or rather this derivative. And I do that by undoing the divided by dx, right? I multiplied both sides by dx to get here. And so that's what we'd put over here. Multiplied by dx, you'd show the work, whatever sounds good. But the whole point with separable differential equations is we have to separate the variables first. On the right side, I see all of my x's, but there's an intruder, there's a square root of y. So we do need to divide off this square root of y to each side. And then I always like to write my variables separate from the differentials. So I wrote that as 1 divided by the square root of dy times dy equals x times dx. This is usually worth 1 point on a free response question. In fact, this type of problem, this separable differential equation, is almost always the section of a free response that is worth the most points out of any other free response on the exam. We've talked about how there are 6 free responses on there. Each free response usually has about 4 parts, A through D. So 6 times 4, 24 different parts. Out of the 24 different parts, if one of those parts is a problem like this, it's usually worth between 4 and 6 points. Remember, a free response is only 9 points. So they're giving you that this part is the lion's share worth of points. So this is the one problem you never want to skip on the free responses. Sometimes you can get away with skipping one that you're like, oh, I don't really know this, it's probably only worth a point, you don't know the point values, but you can guess as you get better at it. This one is always worth a lot of points, you should never skip it. And look at the first step, we just had to move variables to different sides. Once you have all the y's to one side, all the x's to the other, you've already gained yourself 1 point by separating the variables. I went one step further and I rewrote 1 over the square root of y as y to the negative 1/2 because I know what's coming next. If I'm going to write this as an equation in the form of y equals f of x, then we need to get rid of these differentials. And to do that, we've seen it before, we're going to introduce an antiderivative symbol, an integral symbol, an indefinite integral with no endpoints. What does that mean? Well, it tells us that we need to take the antiderivative of each side. The left side is the antiderivative with respect to y, and the right side is the antiderivative with respect to x. And as long as they're all the same variable, you just do the antiderivative. There's nothing tricky here. We add 1 to the power, 2 to offset the power, don't forget your plus c. Add 1 to the power, offset the power, don't forget your plus c. However, I put a plus c1 and a plus c2 because these are probably different constants, right? There's no guarantee that whatever adds to this side is also adding to this one. Depending on the graph and the initial condition, the constants could be different. But then, here's the cool move. Well, actually, I should backtrack too. No, I will not. So, here's the cool move. If I subtract constant 1, C1, from both sides, it's going to combine with constant 2. And what is a constant minus a constant? Well, it's another constant, and you could call it C3, but since I haven't just used plain old C yet, I figured I'd write that as C. Will that happen every time? Well, certainly. There'll be a constant on this side, a constant on this one, and you can always move the constant over. And so actually, when we do the antiderivative of each side in these separable differential equations, we always skip this middle step and we go straight to here. We don't put a plus c on the left side. We do put a plus c on the right side. This constant is like a super constant. It's containing both of these constants over here. Differential equations do weird things with constants, and we'll see more of that next class too. But for now, just worry about putting the plus c on one side. Does it matter which side? No, you could put it on the left side or the right side, or you could do both if you wanted. Once we get to the initial condition, you'll get the same answer every time, no matter where your constant is. By the way, this next step, having taken the antiderivative of each side, is worth between 1 or sometimes 2 points. Depends on how complicated the antiderivatives are. They might say, ooh, each side was really complicated, 1 point for each side. However, sometimes they're just pretty basic, and so it's just 1 total point. So once we've taken the antiderivative of each side and established that plus c, and you do have to write the plus c, there's only 2 steps left. At some point, you will have to isolate y. It has to be in the form of y equals everything else. And you also need to establish the value for c. And there is going to be a value here because these differential equations always come with an initial condition. We've seen that before too, and actually I usually prefer to solve for c first. Some other teachers will teach it where you isolate y first and then you solve for c, but I found since c is just adding at the end, it's pretty easy to isolate that, as opposed to if you solve for y first, it kind of traps the c in and things get a little trickier. So let's use the initial condition, right? We're going to substitute the output in for y and the input in for x. And there's nothing bad here. Square root of 25 is 5. 5 times 2 is 10. This is 9. 9 halves. right? And then we just have to subtract to isolate c, right? We subtract 9 halves from each side. 10 minus 9 halves, treat that as 20 halves. 20 minus 9, c is 11 halves. Okay. Finding the value of c gets you another point. Now we just have one last piece to accomplish. And my last piece to accomplish is to isolate y. There are only two operations acting on y. There's a 2 that's multiplying and there's a 1/2 power. So I went ahead and multiplied both sides by 1/2 first. That's how we get down here. And then to undo a 1/2 power, that's just a square root. So we can square each side, right? A square multiplied by a 1/2 power, or a square and a square root, undo each other and gives us our final answer. This is the last point. Is there a lot of work here? Yeah, but you'll find that it goes pretty darn quickly, right? The first part is just take the antiderivative, don't forget a plus c. Second part, pure algebra, solve for c. The last part, pure algebra, isolate y. So a lot of algebra here, a decent amount of work, but it's not that bad. And I think you'll find as we go through and practice together, you'll be quite successful. Okay, just some concluding notes here. If an FRQ involves a separable differential equation, they're usually 4, 5, 6, 7 would be maybe aggressive. Yeah, I'd probably say between 4 and 6 points tied to the solution depending on how difficult the problem is. This means solving a diff-EQ, a differential equation, is a large percentage of points for a single free response because there are only 9 total points on a free response. And so if one part of it has 6 out of the 9, honestly, that's all you need to get a 5. I mean, that's pretty wild right there. Do not skip separable differential equations. Don't do it, don't do it, don't do it. Separate the variables. Integrate each side. Don't forget the plus c. Use the initial condition to find the value of c, and then isolate y. Okay, let's practice. So, as I mentioned before, many of these problems are ones that you should already know how to do. For example, on AB 2018 question 6, part A is a slope field. I'm not going over the slope field. We did that last class. If you want to check your answer, you can check it with mine. Part B, same thing. We did this last class. It's just a tangent line. You can do it. But are we going to do part C? You betcha. So I would suggest you kind of pause here, work through the first couple. It gives you a good idea of the problem. And then when you're ready, try part C on your own, and then if you get stuck or when you're ready to check your answer, unpause and we can do part C together. Alright, part C. Find the particular solution in the form of y equals f of x to the given differential equation. So our given differential equation was 1/3 x and was y minus 2 squared. Y minus 2 squared. With the initial condition of 1, 0. Alright, here we go. This is the big one. They want a solution. This is our separable differential equation. Do you remember the first step? Move all the variables to one side. So I'm going to go ahead and do 2 steps at once. I'm going to multiply the dx to the right side and divide the y minus 2 squared to the left side. So that gives us 1 divided by y minus 2 squared. dy is still here. Multiplying the dx, we'll move that onto the other side, 1/3 x dx. Sometimes I get students that ask, wait, where do we move the 1/3? Should we multiply by 3 and move it to the other side? I would say generally leave it alone. However, my more specific rule is move the 1/3 to whichever side has an easier antiderivative. Since it's just a constant, we might as well keep it on the easy side. And I think the antiderivative of x will be a lot easier than the antiderivative of that guy. Now, we do need to take the antiderivative of each side to get rid of those dx's and dy's. So you can just slip an integral symbol in here. There's nothing wrong with that. I'm going to rewrite it though, because I know that I'm going to have to rewrite this expression anyways as y minus 2 to the negative second. So I'm just taking that quick extra step, and I'm also going to factor out the 1/3 because that's not going to affect anything either. Okay, let's do our antiderivatives. If you'd like, we can start with the right side, but I think the left isn't too terrible. We need to add 1 to the power. And then what has to go in front to offset the negative 1? Oh yeah, an extra negative 1. The right side, the 1/3 doesn't change. X becomes 1/2 x squared. Oh, and don't forget the plus c. Now, some people at this point ask, wait, this 1/3 was outside the entire integral. Should I put parentheses around that? Yeah, probably. But guess what happens? I'm going to rewrite this left side again. -1 divided by y minus 2 to the first. I guess I don't even need parentheses there. Equals, when I distribute the 1/3 inside, it becomes 1/6 x squared. But 1/3 times a constant is just a constant. It's kind of like a super constant again, if you will. And so I'm just going to keep it as c. So should you write them? Yeah, probably. But would you be wrong if you wrote this? Strangely not, because this will give us the same answer here. So take it as you will. All right, at this point in our free response journey, we've already gained 2 or maybe 3 points. 1 point for separating the variables, and then 1 or 2 more points for the antiderivatives. The next part, and I usually split my paper into 3 sections here, the next part is using the initial condition, right? My initial condition given to us is that f of 1 is 0, or if you write it in coordinate form, 1, 0. So let's start with our -1 divided by, I'll leave the y blank here, 1/6 blank plus c. We know the input is 1, the output is 0, and now we start isolating c. All right, it looks like on this left side I have -1 over -2, which is positive 1/2. 1 squared is 1, that gives us a 1/6 plus c. And then I think we need to subtract 1/6. So if I'm subtracting 1/6 from the left side, we want to combine those together, common denominators, right? So 3/6 minus 1/6, I'm getting that c is 2/6, or if you'd like, 1/3. Now what? Last column. Like I said, generally 3 columns. 1 column for the first couple points, finding c is another point, and the last column is going to actually be the isolating y part. So we're going to start with the actual equation, -1 divided by y minus 2 equals 1/6 x squared plus 1/3. And this is the right solution. It's just not written in the right form. We do need to isolate y from here. Easiest thing to do first, I think, is to distribute the negative to everything. 1 divided by y minus 2 equals -1/6 x squared minus 1/3. Now, from here, you have at least 3 different options to isolate y. Okay, I'm going to give you my favorite way to do it first, and then I'll give you a couple other ways to do it after. Okay, so here's my favorite way. I know eventually I want the y's to be on the top of the fraction, which means eventually I want to flip this fraction. And one of these algebraic techniques that a lot of students forget is that you are allowed to just flip a fraction over as long as you flip the entire other side. Really what we're doing is we're raising this to the negative first power. That causes the reciprocal of a fraction. But we can't flip individual fractions. So what I actually like to do is if I know I want to flip the fraction, I combine these 2 fractions together. So it looks something like this. 1 divided by y minus 2 equals, we'll go -x squared over 6, common denominator, so minus 2 over 6, right? There we go. And then I'm going to put that together. 1 divided by y minus 2 is -x squared minus 2 divided by 6. Now that we have 2 fractions, let's flip them. Y minus 2 over 1, but I don't need the over 1, so that's excessive, equals 6 divided by -x squared minus 2. Is it pretty easy to isolate y now? I hope so. Y equals 6 over, if you don't like all the negatives, you could factor the negative out front and turn the denominator positive, but then when we add the 2 over, just plus 2 at the end. And there we go. I've found that students really like the idea of doing the reciprocal of both sides, but don't forget though, we can't do individual reciprocals. If you flip those 2, the denominators are going to be off and it won't work. I did promise you some other ways to do it though, so let's look at a couple others. I'll start here again. Okay, 1 divided by y minus 2 equals -1/6 x squared minus 1/3. Well, if you want to be really lazy, okay, you can treat this as a fraction And then you can flip the fraction straight away. So it becomes y minus 2 over 1 equals 1 over negative 1/6 x squared minus 1/3. And then add 2 to both sides. Okay, mathematically this is correct. It's gross, but you are not graded on how gross or ungross your answers are, and so that would be fine too. If you wanted yet another way to do this, right? If you had 1 divided by y minus 2 equals negative 1/6 x squared minus 1/3, you could say, I hate the y being in the denominator there. I want to multiply both sides by y minus 2. And that's allowed, right? Again, maybe not the prettiest, but it's allowed. And then you could say, yay, now my y minus 2 isn't in the denominator. Let's divide off all the x's. 1 divided by negative 1/6 x squared minus 1/3 equals y minus 2. And then add 2 to both sides. You get the same thing over here. There are even other ways to do this as well, but I just wanted to give you a few options and reiterate that it doesn't matter how simplified your answer looks. It doesn't matter if it looks different than the rubric. As long as you've made no algebra mistakes, all of these answers are considered the same. Alrighty, we're moving on to 2017. The first couple parts of this are a little bit tricky, and we may have to go over those as a class later on. Don't forget though that my solutions are posted, so you should take a look at those. We are going to jump all the way down to part C. Oh, this pesky potato. For any time that's less than 10, an alternate model for the internal temperature of the potato is the function g that satisfies the differential equation. So they're saying there is some function g that will tell us the internal temperature of this potato, and we only know the differential equation dg dt. Find an expression for g of t. It's a fancy way to say solve using separation of variables. Okay, well, let's rock and roll. You will actually want to divide your paper into 4 parts this time. Having done this problem several times, I'm going to try to save you space, or maybe even just a separate piece of paper. This wins the award for most stuff asked of an AP student on a single free response question that I can ever think of. There are many steps here. So let's work through. We're going to start by using our separable differential equations. I'm going to write kind of small here too because I don't want to run out of room, and hopefully you guys can make this work. So dg dt equals negative capital G minus 27 to the 2/3 power. Okay, first step of separable differential equations, separate your variables. dt is here, we want it on the other side. G is here, we want it on the other side. So I'm just going to start with that dt. So dg is equal to negative g minus 27 to the 2/3 times dt. We're almost there, but the g's aren't on the same side, so I need to divide this off. But then students say, well, wait, if you divide that off, there's nothing left on the right side. And that's not quite correct. When you divide something by itself, there's not nothing left. Nothing would imply 0. Something divided by itself makes a 1. So there is a 1 there. We usually don't write the invisible 1, but if there's nothing left on that side that we can see, we do need the invisible 1. Now what I found helps students is I just say, don't forget there's an invisible negative 1 here. So when you divide off that g minus 27 to the 2/3 on both sides, and we'll do it over here as well, okay, these do cancel or undo each other, but there's still a negative 1 there, and that seems to set people's minds at ease. They're like, oh, there is still a number there. I'm also going to rewrite this g minus 27 to the 2/3 by moving it up. So we end up with, let's try here, g minus 27 to the negative 2/3 dg equals negative 1 dt. I found, and I was teaching at this point, my students really did not do well on this problem. And I'll take some of the blame. I think we didn't do enough practice here, so now I make sure that we do a bunch of these where something disappears. I find almost all of mine forgot that they could put in that invisible 1, and so they didn't get past this first step. And unfortunately, on a single part of a free response, usually you have to get all the points to move forward. So if you don't get the first step, you generally don't get the rest. And that's a lot of points to miss out on. I felt bad. One student got it though, so that was cool. So what do we do from here? I'm just going to slip in that integral symbol, and we'll find our antiderivative. I think the antiderivative of the right side isn't bad at all, right? With respect to t, the antiderivative is negative 1t, because the derivative of negative 1t is negative 1, not forgetting the plus c, right? Our variable matches that d whatever. This left side is a little trickier, but it's not too bad. We have g minus 27. We add 1 to the power. That's positive 1/3. Then what's going to cancel out the 1/3? Oh yeah, a 3. All right, hard part done, I promise. Now let's get to the easier stuff. Okay, next up, we need to use that initial condition. 4 parts. Do I have enough room? 2, 3, 4. There we go. Initial condition. We are given that g of 0 equals 91. When we input 0 into our g function, the output is 91. Means g is 91 and t is 0. Okay, so we have 3 times 91 minus 27 to the 1/3 power equals negative 1 times 0 plus c. Well, right side becomes c. 3 times, don't forget a 1/3 power is the same as the cube root. 91 minus 27, I think, is 64. And we should know the cube root is 64. What times itself 3 times is 64? Well, that's 4. And then 3 times 4 is 12. Now, some people in the past have said, whoa, 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 this wasn't a calculator active problem and we had to know a cube root. And the answer is yes, you are expected to know that cube root. However, if you don't, and here's a cool fact, you could actually keep the cube root of 64 in your answer. And if you said c is 3 times the cube root of 64, you would get 100% full points. That is correct. So there is a way around it, but should you know the cube root of 64? Yeah, you probably should. But if you don't, it's okay. There's still hope for us. All right, what's next? Well, we're going to jump back to our equation, but now we know the value of c. 3 times g minus 27 to the 1/3 power equals negative 1t. That's just negative t, isn't it? We can keep the 1 though. Plus 12. Last part of this is we need to isolate g. First step, divide both sides by 3, right? If we divide by 3, g minus 27 to the 1/3. I'm going to think of multiplying by 1/3. So that gives me negative 1/3 t. And then 1/3 of 12 is 4. Well, next we need to undo the 1/3 power, but if it's a cube root, what undoes a cube root? Oh yeah, a cube. Or you could think of raising both sides to the 3rd power, and that's what I'll do here. So g minus 27 will be negative 1/3 t plus 4 cubed. And hopefully we can see the last step. Just add 27 to each side. Leave a little space here for a second. Negative 1/3 t plus 4 cubed plus 27. And there's our answer. Whew! Decent amount of work there. Some big numbers, some cube roots. You could call this g of t or just g. Doesn't matter one way or another. Once the output is isolated, you can switch to function notation. Great. So are we done? Well, hopefully you said no because I made you write a 4th column over here. And also hopefully you said no because you read the last sentence. Based on this model right here, what is the internal temperature of the potato at time t equals 3? So not only did you have to solve this separable differential equation, you also have to use it to approximate the temperature at a time of 3. Luckily, that's not terrible. G of 3 is equal to negative 1/3 times 3 plus 4 cubed plus 27. And now it's just a little bit of arithmetic, right? Negative 1 plus 4 cubed plus 27. And we continue to simplify down. 3 cubed plus 27. I think 3 cubed is 27. So we have 2 27s, which gives us a final answer of 54. Whew! Lots to do here. This was worth a ton of points. It was an overall quite tough free response question. But hopefully you're getting the idea of these separable differential equations. Variables on each side, so we separated them. Integrate each side, find the value of c, isolate the output. Okay, let's keep moving on. 2015 question 4, same idea. We're actually going to do A here, and then we're going to talk about D as well, because D is a little bit wild. In fact, actually, I think what will make this one easiest is if we do all of these, because this is a weird question. More recently, they've started throwing some strange differential equation questions at us, and so it's probably worth seeing the variety. So we will do all of these. Okay, we're given a differential equation, dy dx equals 2x minus y, and then we have part A. Let y equals f of x be a particular solution. That's our giveaway, separable differential equations, with the initial condition f of 2 equals 3. Either find the particular solution or state why it cannot be found using separation of variables. That's a weird one, but yeah, let's go ahead and start solving. So we have our dy dx equals 2x minus y. Go ahead and pause this for a quick second and see if you can isolate all the x's on one side and all the y's to the other. Give up, or were you able to do it? If you were able to do it, I applaud you, because I'm not quite sure how to do it. Normally when I see students do this, I see them kind of break some rules of math and they like add their dx over to the other side. But the only way you can remove that dx is by multiplying. And when you multiply it, it locks in everything on the right side. So this gives us dy equals 2x minus y times dx. And then we certainly cannot just add y to each side over here, because that's trapped within the parentheses. We're now adding something out of multiplication. And then it would be really weird if you could. It'd be y plus dy. And we don't know how to integrate that guy, right? Y plus dy, we know y times dy, but that plus is a no-go. And so in this case, when we have two terms separated by addition or subtraction, I think we are not going to be able to isolate the variables on each side or separate the variables. So it cannot be found using separation of variables because we cannot separate the variables on each side of the equation. Well, what else are they going to ask us to do then? Well, first they want us to find the second derivative in terms of x and y. Okay, well, let's look at that. So we have dy dx, and we've done this a few times now, equals 2x minus y. If we're going to find the second derivative, we need to do ddx of each side. Right? Nothing bad there. Okay, so this gives us, and I'll work down below, the second derivative of y with respect to x is, well, the derivative of 2x is 2. The derivative of y with respect to x is dy dx. Can we stop there? Well, they said find d squared y over dx squared in terms of x and y, which means this is, and maybe I should write it like this, our second derivative has two inputs, and the two inputs are x and y. Does this have those inputs? No, it doesn't have either of them. It has a different input. It has dy dx. So this expression is not in terms of x and y. And so we need to go further. How do we replace dy dx with only x and y? Oh, well, they told us that in the original problem. Dy dx is defined as 2x minus y. And if we distribute that out, 2 minus 2x plus y. There's our second derivative. They also want us to determine the concavity of all solution curves, so all the curves in y equals f of x, for the given differential equation in quadrant 2. Well, quadrant 2, let's just kind of sketch a cute little graph of quadrant 2 over here. Quadrant 2 is the guy that's over here, right? Let's think about any point in quadrant 2. I'll pick this one. Well, this point, let's pick some numbers on here. Doesn't really matter. Let's say that this is the point -2, 3. Pretty representative of any point in quadrant 2. In particular, the x-coordinate is negative, and the y-coordinate is positive. And I think any point you pick in quadrant 2, not on the axes, in quadrant 2, will have a negative x and a positive y. So what does that tell us about d squared y over dx squared? Well, we know that we're going to take this equation and we're going to be substituting in a negative value for x and a positive value for y. And using the equation we just found, it becomes 2 minus 2 times a negative value plus a positive value. which really becomes 2. A negative times a negative is a positive, plus something else. Won't this always be positive? I think so, because that negative value reverses the sign here, and so we can say that the second derivative is always positive. And if the second derivative is always positive, what does that tell us about the concavity? We are always concave up. So you should write a quick sentence, right? You would say something like concave up because this guy is greater than 0, and that would be fine. All right, third one. Let y equals f of x be a particular solution with the initial condition f of 2 equals 3. Does f have a relative min, max, or neither at x equals 2? Well, this is also kind of a wild problem, because to find mins and maxes of an equation, don't you have to take the derivative of that equation? Oh, but we already know the derivative of that equation. It's up here. How exciting. So we know the derivative is dy dx equals, and they told us it was 2x minus y. Awesome. Well, what do we do next? Well, normally we would set the derivative equal to 0. Except they already told us this point. They're saying we think the point 2, 3 is a relative min or a max, or possibly neither. Well, the first thing we need to remember for a relative min or max is that a relative min or max must be a critical point. How is a point a critical point? Well, it causes the derivative to become 0 or undefined. So I would say let's check this point in the derivative and see if it is a critical point. Let's find dy dx of the point 2, 3. That gives us 2, replace the x with 2, the y with 3. 4 minus 3 is 1. My slope, my derivative at 2, 3 is 1. Can that be a critical point? No, the slope would have to be 0 or undefined. And so it cannot be a relative min or max because this point is not a critical point. And so we'd conclude with neither at x equals 2 because 2, 3 is not a critical point. All right, last one, and this is a wild one. Oof, always throws me for a loop. There are a few ways to do this problem, and I wanted to go through and show you my favorite way. It is different than the way that's on the rubric for, when was this, 2015? Oh, I remember when this problem came out too. That was a rough one. So it's different than what was on the rubric, but I think it makes a little more sense to me. So they want us to find a solution to this differential equation. And you might be saying, but how? We can't do the antiderivative. We can't separate the variables. The only technique you taught us doesn't work. Well, they were very clever with this. Find the values of the constants m and b for which y equals mx plus b is a solution. So what they're telling us is, if you were able to solve this, one of the solutions is in the form of y equals mx plus b. So we're starting with dy dx equals 2x minus y, and they're saying if you're able to solve this, if you're able to take antiderivatives and do all that, the answer will be, when you finish isolating y equals mx plus b, or y equals some value times x plus some value at the end. How does that help us solve? Well, it really comes back to knowing properties of this equation. Hopefully you recognize y equals mx plus b is a linear function. It makes a line. What are some properties that we know about lines? Well, one property is that it has the same slope everywhere. And so you could use the first derivative and try and work with m and try to isolate some things, plug some other things back in, and it will get you there. But what I found, what I think is the easiest way to do this, is to remember something else about a line, and not with regards to the first derivative, but with regards to the second. Since we had to find the second derivative, and we found that it was the thing I forgot, 2 minus 2x plus y, okay, we know that the second derivative measures the concavity, and the concavity is like the flexiness, the curvature of a function. How curved is a line? Oh, that's right, not at all. So if this line is a solution, it means that there is no concavity, or that the second derivative must be 0. What are we going to do now? Well, we know the solution's in the form of y equals stuff with x. If we solve for y here, are we done? Let's try it. If you add 2x to the left side and subtract 2, that gives me positive 2x minus 2 equals y. And yeah, I think we're actually done. The only way the second derivative can be 0 is if y is 2x minus 2. Think of substituting that in. Everything will cancel out, right? And so we have found the values for m and b. M is 2 and b is negative 2. There is another way to do this just with the first derivative and a couple substitutions and systems of equations, but I liked this way the most. All right, let's continue on. 2013 question 6. Again, I'll be skipping a few of these. A is a tangent line. No, thank you. But B, yeah, let's do B. This is actually our second to last one, I think, if this ever loads. So yeah, let's go ahead and tackle B. Find y equals f of x, the particular solution that passes through 1, 0. Again, you guys should do this on your own. And once you've tried it, come back to me. Alrighty, so probably 3 columns again. I bet we won't even need 3 columns because I actually gave you enough space here, but that's fine. So dy dx equals e to the y times 3x squared minus 6x. If we're finding the solution, we need to solve. We're going to have to separate our variables. I'm going to divide by e to the y on both sides and also multiply by dx on both sides. Before I slip in that antiderivative, that integral symbol, I am going to rewrite e to the y, e to the negative y. I think that'll be a little bit easier to take the antiderivative. And then let's throw those integral symbols in. Right? This first step right here, 1 point already. Antiderivative time. Right side looks less intimidating. X cubed minus, this is x squared, 2 times what is 6, 3. And don't forget your plus c. E to the negative y. Some students get freaked out by this y over here, but as long as the variables match, if you'd like, you could just treat this as, the antiderivative of e to the negative x dx. It's the same thing, it's just a different variable, as long as they match. So, we know that e is always itself, so this won't change. And then we check, is the derivative of this itself? And it almost is itself, but it'll be itself times the derivative of the power, and the derivative of negative y with respect to y is just negative 1. I don't see a negative 1 here, so we need an extra negative 1 to cancel everything out. Cool. We're already done with the first part. Told you we probably wouldn't need all the columns, but I'll use them anyways. Let's go ahead and move on to our initial condition. We know that it must pass through the point 1, 0, so negative 1 times e to the negative 0th equals 1 cubed minus 3 times 1 squared plus c. Okay, negative 1, e to the 0th power is 1. This is 1 minus 3 plus c. Negative 1 equals negative 2 plus c. It's looking to me like c is 1. Last step, we have negative 1 times e to the negative y equals x cubed minus 3x squared plus 1. Well, I'm definitely going to divide that negative 1 over to the other side, so negative x cubed plus 3x squared minus 1. And then we need to undo e. Do we remember how to do that? Natural log, right? We have to do that on each side. They undo each other. Leaves me with negative y equals the natural log of negative x cubed plus 3x squared minus 1. And then, if you really want to be lazy, just move the negative over. Look at that. We're set. Okay. Could you check that answer? Well, certainly. Take the derivative of everything there and then see if you can manipulate to get back here. A little bit of work, but it is doable. All right. Last one, I think. Slope field to start, you can do that. There is a horizontal line with the equation y equals c that satisfies this differential equation. Oh yeah, we should probably talk about that one. That's a pretty cool one. So they're saying if you were able to solve this, there is a solution that's just y equals c. Now if you sketch a cute little graph over here, we should know that the equation y equals c is linear. And in particular, y equals something without an x is actually horizontal. So doesn't that mean that our line is just going to go straight across? What are properties of horizontal lines? Well, don't they have no slope? Or I guess particularly they have a slope. They have zero slope. And luckily we have a differential equation which describes the slope of all the points there. So to figure out our solution, let's start by setting the slope equal to 0. Okay, not bad. From here, I think we have two equations, right? This is in factored form. Y minus 1 squared equals 0, or cosine of pi x equals 0. And you might get very scared. You're like, oh, I don't want to solve this cosine one. You don't have to. They want to know the y value. Y equals what satisfies. This has an infinite number of solutions, which means there'll be an infinite number of x equals something. However, we want y equals, and this one's really easy. I think it's just y equals 1, isn't it? And that's it. Y equals 1 will satisfy the differential equation. And you'll actually notice when you made your slope field at 1, there were 0 slopes, because this line will satisfy that differential equation. All right, part C. Find the particular solution. Separable differential equations. Here we go. 3 columns again. And we begin. So we start with our differential equation. This is y minus 1 squared times the cosine of pi x. Let's start moving things around. 1 divided by y minus 1 squared dy equals cosine of pi x dx. Integral symbol, I'm going to move this up though. Easier to take the antiderivative with that negative power out of a fraction. Same thing on the other side. Antiderivatives. We already did the one on the left. We increased the power by 1, -1 to offset it. The right one's a little trickier. I know cosine is going to become sine, and I know the inside won't change. There's also a plus c. Then the question becomes, does this match? Well, the derivative of sine is cosine, and if the inside stayed the same though, that would mean because of this inside, we'd be multiplied by the derivative of the inside. The derivative of 4x is 4, the derivative of 10x is 10, the derivative of pi x is pi. But since I don't see a pi there, something must have canceled it out. There had to have been a 1 over pi out front. Okay, from here we have found our antiderivatives. Now we need to use that plus c. I'm actually probably going to go a step further here too. I'll rewrite this as, since I have the space, -1 divided by y minus 1 equals sine of pi x over pi plus c, just saving us some space. Okay, initial condition. We know we have the point 1, 0. So -1 divided by 0 minus 1. I find students tend to switch the x's and the y's here. Be careful with that. You know the y is the second coordinate. Equals sine of pi times 1 divided by pi plus c. -1 over -1 is +1. This is just sine of pi, and sine of any pi, full pi value is 0, I think. So it looks like c is 1. That was nice and easy. Okay, last part. -1 divided by y minus 1 equals sine of pi x over pi plus 1. Okay, 2 steps in one. I'll get rid of the negative first by moving it over. 1 divided by y minus 1 equals negative sine of pi x divided by pi minus 1. But instead of 1, since I know I'm going to have to flip this 1 over y minus 1, I'll rewrite 1 in terms of pi. Pi over pi is the same as 1. Combining those together, negative sine of pi x divided by pi, extend the fraction, common denominators, minus pi. Now we flip our fractions. Reciprocal of each side, y minus 1 over 1 is going to be equal to pi over negative sine of pi x minus pi, and then finish adding the 1. If you really want to be awesome, you can recognize there's a negative to both of these and factor the negative out to the front of the fraction. You can totally keep the negative inside, it does not matter. Plus 1. And there we go, our solution. The more you practice these, and we'll do a bunch again next class too, the more confident you're going to feel. They are so important. They are the most point holding part of any free response. So if you see one, get ready for a bunch of steps, but also get ready to earn all 4, 5, or 6 points on that problem. Thanks for tuning in. We have one more lesson here, also focuses on separable differential equations. I'll have you back next class.